Look up at the night sky, really look at it. Those countless stars, each one a sun, many with planets of their own, spinning in the endless dark. Now consider this, for all that vastness, for all those billions upon billions of worlds, we've never once heard a confirmed whisper from another civilization. Not a single hello, not a crackle of alien radio, nothing. That silence is terrifying or thrilling depending on how you see it. Scientists call it the Fermi paradox. If the universe is so unimaginably huge and so unimaginably old, where is everybody? Shouldn't the cosmos be buzzing with voices? Yet, what if the signals are already here, floating through space like cosmic breadcrumbs, and we just haven't recognized them all yet? That's the tantalizing mystery we're diving into today. Across decades of listening, astronomers have picked up strange, unexplainable blips, radio bursts repeating in patterns too precise to ignore, signals that vanish as suddenly as they appear, even eerie transmissions that seem to carry mathematical precision. Some might be natural phenomena colliding stars, pulsars, or cosmic static, but others defy easy explanation. Could these be the faint echoes of civilizations far older, far stranger than our own? This isn't just science fiction. It's real science, real data, and real curiosity driving the search. Today, we're counting down 25 of the most baffling, electrifying signals ever detected, each one a potential handshake from the unknown. Some were dismissed as glitches, others remain stubbornly unexplained, and a few have sparked debates that stretch for years. What if one of them is the real deal? What if, right now, as you're listening, a message meant for us is streaming through the void, waiting to be decoded? Strap in. The universe might be far louder and far stranger than we ever imagined. One night in August 1977, a radio telescope in Ohio picked up something extraordinary, a signal so powerful and unusual that the astronomer who discovered it scrawled, "Wow." In red ink on the printout, that moment became legendary. The wow signal lasted exactly 72 seconds, blasting through the hydrogen line frequency, a band scientists had long theorized aliens might use for communication. What made it special? It wasn't just the strength, 30 times louder than the cosmic background noise, but its precision. The signal was narrowband, meaning it occupied a tiny, focused slice of the radio spectrum. Natural cosmic noise is messy, scattered across frequencies. This was like hearing a pure, steady whistle in a hurricane. Here's the strangest part: it never repeated. Despite decades of searching the same patch of sky near the constellation Sagittarius, silence followed. Some argue it was a passing comet, but comets don't emit narrowband signals. Others suggest satellite interference, but no known human activity matched its profile. The mystery only deepens when you consider the math, that 72-second duration. That's exactly how long the telescope's fixed gaze would have captured a distant, unchanging signal as Earth's rotation swept it into view, and then out again. Almost as if it was designed to be noticed just once. Could it have been a cosmic flare, a glitch, or something else entirely? Maybe, but the fact that it ticks every box for an artificial transmission, the right frequency, the right duration, the right intensity, keeps the debate alive. Astronomers still scan that patch of sky, hoping for another whisper. Meanwhile, the original wow notation sits in an archive, a single red mark on a sheet of paper, holding one of astronomy's greatest unanswered questions. The wow signal refuses to fade into obscurity. Decades later, astronomers keep circling back to it, armed with better technology and sharper questions. One compelling theory suggests the culprit might have been a comet specifically. Two comets, 266P and 2667P, discovered years after the signal was detected. These icy wanderers happened to be passing through that exact patch of sky in 1977. Comets release hydrogen as they vaporize in sunlight, and hydrogen emits at the same frequency the WOW signal used. Could it have been a cosmic coincidence? Skeptics point out a critical flaw. Comets spew hydrogen in wide, messy clouds, not the razor-sharp narrowband burst the telescope caught. Then there's the human angle. Could satellite transmissions or military experiments have mimicked an alien signal? Declassified documents reveal Cold War-era projects testing powerful radio bursts, but none match the WOW signal's unique fingerprint. No known human-made source at the time could explain its intensity or that precise frequency. Even today, with our crowded skies full of satellites and drones, nothing quite like it has been recorded again, yet some scientists still lean toward the extraordinary. The signal's brevity and precision mirror what we'd expect from an intentional transmission, a deliberate, one-time beacon perhaps aimed our way. Imagine a civilization flicking a cosmic flashlight in our direction just once to see if anyone notices. The WOW signal's location adds another layer of intrigue. It came from near a star cluster packed with sun-like stars, prime real estate for habitable worlds. New tools might finally crack the case. Projects like Breakthrough Listen now scour millions of radio channels simultaneously, hunting for echoes of that iconic WOW. If the signal repeats, we'll know it wasn't a fluke. Until then, it lingers in that tantalizing gray area, too strange to dismiss, too rare to confirm. Whether it's a comet's cry, a human hiccup, or something far more profound, one thing's certain: that 72-second burst rewrote the rules of the cosmic conversation. And if we ever hear it again, the universe just got a whole lot louder. Fast radio bursts are among the most puzzling phenomena in the cosmos, blindingly bright flashes of radio waves that vanish in milliseconds, releasing as much energy as the sun does in days. For years, astronomers assumed these were one-off cosmic accidents, the death cries of colliding neutron stars or evaporating black holes. Then came FRB 121102. Discovered in 2012, this wasn't just another fleeting blip, it repeated, and not just once, but over and over in unpredictable patterns, rewriting everything we thought we knew about these mysterious signals. This particular burst originated in a tiny, unassuming dwarf galaxy 3 billion light-years away, a place with far fewer stars than our Milky Way, making it an odd home for such a powerful, repeating event. The galaxy itself is weirdly active, birthing new stars at a frantic pace while also harboring a persistent radio source, likely a supermassive black hole. But here's where things get even stranger. While most fast radio bursts flicker and die, FRB 121102 has been sputtering out signals for years, sometimes quiet for months before suddenly erupting in a flurry of activity. The pattern doesn't match any known natural process. That inconsistency has led some researchers to propose a far more radical explanation: technology. Advanced alien technology. The bursts could be leakage from colossal energy beams. Imagine a civilization harnessing the power of a black hole to propel light sails across galaxies, or perhaps a beacon system deliberately broadcasting into the void. The signal's intensity fits. A transmitter the size of a planet powered by a star's worth of energy could theoretically produce such flashes, and the irregular timing. That might be intentional, a way to stand out against the natural chaos of the universe. Of course, there are less sensational theories too. Magnetars, neutron stars with unimaginably strong magnetic fields, could be responsible, their surfaces cracking under magnetic strain to produce these explosive bursts. Yet even this explanation stretches our understanding of physics. No known magnetar in our galaxy behaves quite like this, and none have been spotted in the host galaxy of FRB 121102. What makes this signal so tantalizing is its persistence. While other fast radio bursts come and go, this one lingers, offering scientists a rare chance to study it in depth. Telescopes have caught it mid-burst, revealing complex structures within the signals, strange subpulses and frequency drifts that hint at something far more intricate than a simple cosmic explosion. Whether it's the work of nature or intelligence, one thing's certain: FRB 121102 is rewriting the rules. Every new burst is a clue, and with each one, we inch closer to answering the biggest question of all. Are we listening to the universe's natural symphony, or is someone out there turning the dial? Most cosmic signals flare and fade, leaving astronomers scrambling to catch them before they vanish forever. But repeating fast radio bursts like FRB 121102 defy that pattern. They come back, sometimes sporadically, sometimes in clusters, like a cosmic Morse code operator with terrible timing. This repetition changes everything. One-off bursts could be written off as cosmic collisions or dying stars, but a signal that repeats, that suggests something persistent, something with a cycle, a mechanism, maybe even a purpose. Think of it like hearing footsteps in the dark. A single footstep might be the wind knocking over a chair, but footsteps that keep coming, that's someone or something moving with intent. Repeating FRBs force us to confront the unsettling possibility that we're not just listening to the universe's random noise, we might be eavesdropping on its machinery. The leading natural explanation involves magnetized neutron stars with magnetic fields so strong they could strip the electrons off an atom from halfway across the galaxy. When these stars starquake, their crusts crack under magnetic pressure, potentially unleashing the energy of a billion suns in a radio scream. But here's the catch: magnetars in our galaxy don't behave like FRB 121102. They're messy, unpredictable, and nothing we've seen matches the precise, repeating cadence of this distant signal. That inconsistency has sparked wilder ideas. Could these bursts be powering alien megastructures? A civilization advanced enough might harness such energy to propel starships or communicate across galaxies. Picture a lighthouse beam sweeping past Earth every few months, not aimed at us, but powerful enough to blind our telescopes by accident. Or consider the possibility of a planetary-scale transmitter tapping into a black hole's spin to broadcast messages we can't yet decode. Then there's the eerie timing. Some bursts arrive in tight clusters, others after long silences. If this were natural, why wouldn't it follow a pattern? Unless, of course, the irregularity is the point. Imagine designing a beacon to stand out against cosmic static. You wouldn't pulse steadily, you'd randomize it, ensuring no natural phenomenon could mimic your signal. Yet the most compelling argument might be the simplest: we just don't know. Every time we think we've pinned down FRB 121102, it surprises us. New observations reveal substructures within the burst, tiny chirps and frequency shifts that suggest layers of complexity no current model explains. Whether it's a magnetar's cry, an alien machine, or something we haven't even imagined, one thing's clear: the universe loves a good mystery, and this one's far from over. In 2003, a radio telescope scanning the skies caught something peculiar. A signal defying easy explanation. Coded SHB 02+14a, this faint whisper of radio waves seemed to emanate from a patch of space near the constellation Pisces. What made it stand out wasn't just its origin, but its bizarre frequency hovering around 1420 MHz, a number that should ring bells for anyone familiar with the search for extraterrestrial intelligence. That frequency sits squarely in the water hole, a band astronomers have long considered ideal for interstellar communication, nestled between the natural radio emissions of hydrogen and hydroxyl molecules, the building blocks of water. The signal's behavior only deepened the intrigue. It wasn't constant; instead, it flickered in and out, drifting slightly in frequency over time. Some dismissed it as random interference, perhaps a passing satellite or a glitch in the telescope systems. But the drift was consistent, as if the source itself was moving. Here's where it gets eerie. That drift matched what we'd expect from a signal originating on a planet orbiting a distant star, its motion subtly tugging the frequency like a cosmic Doppler effect. Yet SHGB 02 plus 14 refused to play by the rules. Despite multiple attempts to re-observe it, the signal proved maddeningly elusive. Unlike the WOW signal, which blazed brightly once and vanished, this one teased, appearing just long enough to spark debate, then fading before conclusive analysis. The lack of repetition made it impossible to confirm whether it was a technical artifact, a natural astrophysical oddity, or something far more deliberate. Critics pointed to the signal's weakness and the likelihood of terrestrial interference. Our own technology, after all, floods the radio spectrum with noise. Cell towers, satellites, even microwave ovens can mimic extraterrestrial signals. But proponents countered with a compelling detail: the frequency drift. Natural cosmic sources don't drift in this precise, predictable way. A rotating pulsar or a colliding black hole wouldn't produce this pattern. It's the kind of fingerprint you'd expect from a transmitter on a spinning world, its motion imprinting itself on the signal. Then there's the location. Pisces isn't just another patch of sky. It's a region rich with sun-like stars, some with known exoplanets. If you were aiming a beacon, hoping to catch someone's attention, this wouldn't be a bad direction to choose. But without a repeat performance, the signal remains a tantalizing what if. The story of SHGB 02 plus 14 underscores the challenges of SETI, the search for extraterrestrial intelligence. For every potential candidate, there are 100 false alarms, and even the most promising signals often crumble under scrutiny. But this one lingers in the gray zone, a whisper too strange to ignore, too faint to prove. If it was a handshake from the cosmos, it's one we barely caught and might never hear again. Yet its very existence reminds us the universe is vast, and its quietest signals might be the ones worth listening to most closely. The silence that followed SHGB 02 plus 14 is as puzzling as the signal itself. Despite multiple sweeps of the same region with more sensitive equipment, astronomers have never caught another whisper like it. This absence fuels the debate: was it a fluke, a trick of our own technology, or did we intercept a transmission never meant to be heard twice? The answer might lie in the signal's fleeting nature. Unlike a pulsar's steady heartbeat or a quasar's constant roar, this was a flicker, here one moment and gone the next. One prevailing theory suggests terrestrial interference. Earth's atmosphere is a cacophony of radio noise, air traffic control radars, military communications, even garage door openers can mimic extraterrestrial signals. The Allen Telescope Array, which first detected SHGB 02 plus 14a, sits in California's radio quiet zone, but no location is entirely shielded from human-made interference. Critics argue the signal's faintness and drift could align with a high-altitude aircraft or a satellite on the edge of detection. Yet no known man-made source has been definitively matched to it, leaving the door cracked for more exotic explanations. Then there's the cosmic lottery angle. If the signal was genuinely extraterrestrial, its one-off nature might not be accidental. Imagine a civilization beaming messages randomly across the galaxy, hoping someone somewhere might catch a fragment. We could have intercepted a single pulse in a vast interstellar Morse code, with the rest lost to the void. Alternatively, the signal might have been aimed deliberately, a brief hello from a transmitter that's since fallen silent, either by design or disaster. The lack of repetition also raises practical hurdles. SETI projects often prioritize signals that repeat as they allow for verification. A single blip, no matter how intriguing, is scientifically indigestible. It's like hearing one note of a symphony and trying to reconstruct the entire composition. Without more data, SHGB 02 plus 14 remains a phantom, tantalizing but untestable. Advancements in technology might someday settle the debate. next-generation telescopes like the Square Kilometre Array will scan the skies with unprecedented sensitivity, capable of catching even the faintest whispers. If SHB 02 plus 14 was a cosmic ping, we might finally be equipped to hear the pong. Until then, it lingers in the realm of beautiful mysteries, a reminder that the universe's quietest signals often demand the loudest questions. Before 2007, astronomers thought they had the universe's radio soundtrack figured out: pulsars with their metronomic beats, quasars humming in the background, the occasional static of cosmic collisions. Then, on a routine scan of archival data, Duncan Lorimer and his student David Narkevic stumbled onto something that shattered those assumptions. Buried in observations from the Parkes radio telescope in Australia was a spike of radio waves so intense, so fleeting, it defied all expectations. Lasting just 5 milliseconds, the Lorimer Burst packed as much energy as the Sun emits in a month, and then it was gone. No warning, no echo, no explanation. What made this discovery revolutionary wasn't just the signal's power. It was the realization that the cosmos harbors phenomena we hadn't even imagined. Until then, fast radio bursts weren't a category. They didn't exist in astronomy textbooks. The Lorimer Burst carved out an entirely new field overnight. But with that breakthrough came a frustrating limitation: its one-time nature. Unlike pulsars, which pulse predictably, or even later repeating FRBs, this burst left no trail to follow. It was a cosmic gunshot heard across the universe, with no bullet casing to examine. The signal's brevity posed unique challenges. 5 milliseconds is barely a blink, too short to pinpoint a precise origin, too sudden to capture accompanying light or other wavelengths that might reveal its source. All researchers had was a fingerprint, a telltale smear of dispersion where higher frequencies arrived slightly before lower ones. This dispersion suggested the burst had traveled billions of light years, its waves stretched and slowed by the sparse electrons littering intergalactic space. If true, the energy required to make something so bright visible across such distances was staggering. A neutron-star collision, a black hole's final gasp. Theories proliferated, but without a repeat performance, evidence remained thin. Then came the skeptics. Some argued the burst might be local, a glitch in the telescope's electronics, or even a microwave oven on the observatory grounds. Parkes had a history of picking up terrestrial interference, and for a time, the Lorimer Burst risked being dismissed as cosmic static. But meticulous analysis ruled out human-made noise. The signal's dispersion was textbook perfect for an extragalactic origin, and no known earthly gadget could mimic that fingerprint. The Lorimer Burst's legacy is twofold. It proved the universe hides explosive, enigmatic phenomena we're only beginning to detect, and it set a daunting standard. How do you study something that refuses to show itself twice? Later discoveries of repeating FRBs would offer more data, but the original burst remains a paradox, a flash of brilliance that rewrote the rules, then vanished without a trace. Its greatest lesson might be humility. For all our telescopes and algorithms, the cosmos still holds echoes we can't predict, flashes we can't explain, and perhaps voices we've yet to truly hear. The Lorimer Burst didn't just vanish into the cosmic static, it left behind a seismic shift in how we listen to the universe. Before that 5-millisecond flash, astronomers weren't even looking for signals like it. The idea that space could produce such brief, violent radio explosions seemed implausible, almost fictional. Yet there it was, a crack in the door, forcing scientists to reconsider what the cosmos might be hiding. Suddenly, the search for extraterrestrial signals wasn't just about hunting for deliberate messages. It was about tuning into the universe's raw, unfiltered noise, listening for anomalies that might rewrite the rules of physics itself. This single burst became the Rosetta Stone of a new astronomical discipline. Within years, teams worldwide began scouring old data, uncovering similar flashes buried in decades of overlooked observations. Each new detection confirmed that the Lorimer Burst wasn't a fluke. It was the first glimpse of a widespread phenomenon. By 2013, astronomers had formalized the term fast radio burst, or FRB, to classify these enigmatic events. The field exploded. Today, we've catalogued hundreds, with new ones detected almost weekly. Every detection refines our models, but none have matched the original's tantalizing elusiveness. The legacy of the Lorimer Burst isn't just in the signals, it's in how we hunt for them. Traditional SETI programs focused on narrowband transmissions, the kind a civilization might engineer. But FRBs proved the universe could scream in ways we'd never anticipated. That revelation forced a paradigm shift. Projects like Breakthrough Listen now scan for both artificial and natural anomalies, blurring the line between astrophysics and the search for intelligence. After all, if an alien civilization harnessed cosmic-scale energies, their technology might mimic nature's most extreme phenomena. What's equally fascinating is how the mystery deepened. Repeating FRBs discovered years later offered clues the Lorimer Burst couldn't. But that first burst remains the gold standard for cosmic unpredictability. It's a reminder that for all our advances, the universe still specializes in surprises. Somewhere out there, among the billions of galaxies, forces we can't yet imagine are hurling titanic bursts of energy across the void. And thanks to one 5-millisecond blip, we're finally listening. Radio waves aren't the only way the universe might be signaling us. Sometimes the clues are written in starlight. Enter KIC 8462852, better known as Tabby star, named after astronomer Tabitha Boyajian, who first flagged its bizarre behavior. This unassuming star in the constellation Cygnus doesn't pulse or flare like others. Instead, it dims erratically, dramatically, and in ways no natural phenomenon should. Imagine a light bulb flickering not because of a faulty switch, but because something massive, something unnatural, might be passing in front of it. The mystery began with data from NASA's Kepler Space Telescope, which hunts for exoplanets by spotting the subtle dips in starlight caused when a planet transits its sun. But Tabby's star didn't play by those rules. Its light didn't dip by a tidy 1 or 2%, like a Jupiter-sized planet might cause. It plummeted by up to 22% in chaotic, asymmetrical drops, sometimes for days, sometimes for weeks, with no predictable rhythm. Even stranger, historical data revealed the star had been fading overall for over a century, dimming by an unprecedented 14%. Stars this age don't behave like that. They don't just dim, theories exploded, the most headline-grabbing alien megastructures, specifically a Dyson swarm, a hypothetical cloud of energy collecting satellites or platforms built by an advanced civilization to harness their star's power. The irregular dips could fit the silhouette of such a construct, with vast panels or orbital debris drifting unpredictably across the star's face. It's a tantalizing idea, but scientists urged caution. The universe is weird enough without invoking aliens, and nature often outpaces our imagination. Dust emerged as the leading natural explanation. Observations from the Hubble and Keck telescopes revealed the star's light was reddening as it dimmed, a telltale sign of fine particles scattering shorter wavelengths, just like Earth's sunsets turn red. This suggested a swirling cloud of cosmic dust, perhaps from shattered comets or a catastrophic planetary collision, but even this theory strains credibility. The dust would need to be improbably fine, unevenly distributed, and replenished constantly to match the star's century-long fade. Then there's the star itself. Tabby's star is an F-type main sequence star, slightly larger and hotter than our Sun, but otherwise ordinary. Spectroscopic analysis shows no signs of the violent flares or magnetic activity that might explain such extreme dimming. It's as if the star is being shaded by an invisible hand, its light filtered through a cosmic sieve we can't quite see. Newer studies have added twists. Some suggest the dust might be circumstellar, orbiting the star in a vast, lopsided ring. Others propose a swarm of Trojan asteroids locked in gravitational resonance, casting shifting shadows. But none fully explain the star's long-term decline or the sheer scale of those sudden dips. Even after years of scrutiny, Tabby's star refuses to fit neatly into any box. What makes this puzzle so compelling is its accessibility. Unlike fleeting radio bursts or distant fast radio bursts, anyone with a decent telescope can point it at Cygnus and witness the anomaly firsthand. Citizen scientists have joined professional astronomers in monitoring the star, turning it into a crowdsourced cosmic detective story. Every new dimming event sparks fresh debate, with researchers racing to capture spectra, measure polarization, or hunt for accompanying infrared heat, any clue that might crack the case. Whether it's dust, debris, or something far stranger, Tabby's star has already rewritten the playbook for stellar behavior. It's a reminder that the universe doesn't need aliens to be mysterious, but it doesn't rule them out either. And until we know for sure, that flickering light in Cygnus remains one of astronomy's most tantalizing what-ifs. Now shift the lens further. If Tabby's star teaches us anything, it's that anomalies come in many forms. Some whisper in radio static, others hide in plain sight, written in the ancient light of distant suns. And sometimes the most profound mysteries aren't just about what we hear, but what we see. The idea of a Dyson Sphere isn't just science fiction, it's a serious, if speculative, answer to one of civilization's ultimate questions. How would an advanced society harness the energy of its star? Physicist Freeman Dyson first proposed the concept in the 1960s, imagining a vast array of solar collectors encircling a sun, capturing its radiation to power technologies beyond our comprehension. For Tabby's star, this isn't just a thought experiment. Those erratic, jaw-dropping dimming events fit eerily well with what we'd expect if a civilization were building such a structure, piece by piece, in chaotic orbits, casting irregular shadows as they passed in front of their star. But let's be clear, the Dyson Sphere hypothesis is a last resort, not a first guess. Scientists are trained to exhaust every natural explanation before invoking aliens, and for good reason. The universe is full of bizarre phenomena we don't yet understand, yet Tabby's star pushes those boundaries. The dips in brightness aren't just deep, they're asymmetrical, meaning whatever's blocking the light isn't a smooth, spherical object like a planet. It's jagged, uneven, as if constructed from mismatched panels or debris. And then there's the long-term dimming, as if the star's light is being gradually siphoned away over centuries. Skeptics have compelling counter-arguments. Dust, especially microscopic particles, could explain both the irregular dips and the reddening effect observed in the star's light. But dust usually emits infrared radiation as it absorbs starlight, and Tabby's star shows no such excess heat. Unless the dust is colder than expected or positioned perfectly to evade detection, this leaves gaps in the theory. Others suggest swarms of comets, but the sheer number required thousands, even millions, defies plausibility. What makes the Dyson Sphere hypothesis linger isn't just its fit with the data, it's the audacity of its implications. If even a fraction of the star's light is being harvested, we're glimpsing engineering on a scale that dwarfs human history. Imagine structures larger than planets, built not by nations but by civilizations spanning millennia. The energy demands alone hint at a society far beyond our own, perhaps one that's transitioned from planetary inhabitants to true masters of their solar system. Yet for all its allure, the hypothesis faces brutal scrutiny. A full Dyson Sphere would block nearly all of a star's light, not just 22%. And why would a civilization build something so haphazard, with gaps and inconsistencies, unless, and here's where it gets fascinating, we're seeing a work in progress. A partially built swarm, or one that's decaying over time, could explain the messy observations. It's a stretch, but in the absence of clearer answers, even stretches are worth exploring. The debate isn't settled, and that's the point. Tabby's star isn't just about solving a mystery, it's about learning how to ask better questions. Whether the answer is dust, asteroids, or something beyond our current science, this star reminds us that the universe is stranger, wilder, and more wondrous than we've dared to imagine. And if, against all odds, the answer is intelligence, then the cosmos just got a lot more interesting. In August 2015, a Russian radio telescope scanning the cosmos for signs of extraterrestrial intelligence locked onto something peculiar. A strong, narrowband radio signal emanating from the vicinity of HD 164595, a sun-like star 94 light-years away in the constellation Hercules. Unlike the static-filled noise of most cosmic sources, this signal stood out for its precision. It pulsed at a frequency of 11 GHz, a range with little natural interference, making it an ideal candidate for something artificial. The discovery sent ripples through the scientific community. Here, at last, might be the long-awaited evidence of another civilization reaching out across the void. What made HD 164595 so intriguing wasn't just the signal itself, it was the star. A near twin of our Sun in size and age, it fit the profile of a system where life as we know it might thrive. Astronomers had already discovered a Neptune-sized planet orbiting it, though far too close to the star to be habitable. Still, the presence of one planet raised the possibility of others lurking in the system's Goldilocks zone. If a civilization there had developed radio technology, they might have deliberately chosen this frequency to stand out against the cosmic background. The signal's intensity added to the mystery. To reach Earth with such strength, the transmitter would need to be unimaginably powerful, either a focused beacon aimed directly at us or a planetary-scale broadcast radiating in all directions. Excitement, however, was quickly tempered by skepticism. The signal had been detected only once by the RATIAN 600 telescope in Russia, and attempts to replicate the finding with other observatories came up empty. The Allen Telescope Array in California, trained on the same coordinates, heard nothing. This inconsistency raised red flags. Genuine extraterrestrial signals don't just vanish, they persist or repeat in ways that allow for verification. Without independent confirmation, the HD 164595 signal began to look less like a cosmic hello and more like a ghost in the machine. The break came when researchers traced the signal's origin not to the distant star, but to much closer to home. Further analysis revealed the telltale fingerprints of human-made interference, likely a military or communication satellite passing through the telescope's field of view. The 11 GHz frequency, while unusual for natural cosmic sources, is commonly used by Earth's own technology. The signal's fleeting nature and inability to be detected elsewhere fit the profile of a passing satellite or aircraft, not an alien broadcast. Yet the episode wasn't a dead end. It underscored a growing challenge in the search for extraterrestrial intelligence, our own planet's noise. As Earth's radio environment becomes increasingly crowded with satellites, drones, and wireless networks, distinguishing a genuine cosmic signal from terrestrial interference grows harder. Projects like Breakthrough Listen now employ sophisticated algorithms to filter out human-made noise, but the HD 164595 incident remains a cautionary tale. The universe is vast, but our own backyard is louder than ever. What lingers, though, is the tantalizing question: what if we'd been wrong about the explanation? What if, buried in the static of human interference, there was a whisper of something more? The star itself is still out there, a sun-like beacon in the Hercules constellation, its secrets untouched. Future telescopes, free from Earth's radio clutter, might one day scan it again, this time with sharper ears and better tools to separate the cosmic from the commonplace. Until then, HD 164595 serves as both a lesson and a lure, reminding us that the line between discovery and false alarm is often as thin as a radio wave. The story of HD 164595 isn't just about a signal that wasn't. It's a masterclass in how the search for extraterrestrial intelligence walks the razor's edge between hope and skepticism. False positives like this one aren't failures. They're stress tests for the entire field, revealing both the fragility of our methods and the ingenuity required to refine them. Every dead end forces scientists to ask harder questions. How do we separate cosmic whispers from Earth's cacophony? What does a truly alien signal even look like? These aren't abstract puzzles, they're the daily grind of SETI, a discipline where patience is measured in decades and breakthroughs are often measured in milliseconds. Take the infamous WOW signal as another cautionary tale. For years, it stood as the gold standard of potential contact, its singular burst defying explanation. Yet the more we scrutinized it, the more we realized how much we didn't know about comets, about telescope glitches, about the universe's capacity for mimicry. HD 164595 signal followed a similar script, a tantalizing blip that collapsed under scrutiny, reminding us that the cosmos is full of red herrings. But here's where the lesson gets transformative. These false alarms don't weaken the search, they weaponize it. Each one tightens the filters, trains the algorithms, and sharpens the questions. Modern SETI has evolved into a game of forensic signal analysis. When a candidate transmission emerges, teams now cross-reference it against satellite databases, aircraft trajectories, and even microwave oven emissions. Yes, a running microwave near a telescope once mimicked an FRB. Projects like Breakthrough Listen Deploy Machine learning to sift through millions of frequencies in real time, flagging only the anomalies that pass multiple gates of verification. It's a far cry from the early days when a single blip on a printout could spark global headlines. Now the burden of proof is staggering. A signal must repeat, it must originate from a fixed point in space, and it must defy every known natural explanation. Even then, skepticism remains the default posture, yet there's a paradox here. The stricter the standards, the more we risk overlooking something genuinely extraordinary. What if an alien signal isn't steady or repetitive? What if it's a one-time burst like the Lorimer discovery, or a pattern so foreign we lack the framework to recognize it? This is the tightrope SETI walks, balancing rigor with open-mindedness, ensuring we don't dismiss the very thing we're hunting for. The HD 164595 incident underscores this perfectly. Its frequency was suspiciously human, but had it arrived from a star with no known planets or pulsed in a mathematically significant sequence, the conversation might have gone very differently. Ultimately, false positives are the search's unsung teachers. They force humility, proving that our tools are blunt instruments in a universe of infinite subtlety. But they also fuel persistence. Every dead end narrows the path forward, inching us closer to the day when a signal doesn't fade under scrutiny, when it holds up, defies explanation, and forces us to confront a reality far stranger than fiction. Until then, each false alarm is a stepping stone, a reminder that the greatest discovery in history might begin with a blip we almost ignored. In December 2020, astronomers with the Breakthrough Listen project detected something extraordinary, a narrowband radio signal, clocking in at 982 MHz, emanating from Proxima Centauri, the closest star system to Earth. Codenamed BLC1, this signal wasn't just any blip. It appeared to originate from the same region as Proxima Centauri b, a rocky exoplanet nestled in the star's habitable zone where liquid water and potentially life could exist. For a brief, electrifying moment, it seemed humanity might be on the verge of answering the universe's oldest question: are we alone? The excitement wasn't just about the signal's origin. Everything about BLC1 screamed artificial. Unlike the chaotic bursts of natural cosmic phenomena, this was a pure, steady tone, the kind you'd expect from a transmitter, not a pulsar or flare. Even more intriguing was its drift. Signals from distant stars shift in frequency as they travel, affected by the Doppler effect, and BLC-1's drift matched what you'd expect from a planet orbiting Proxima Centauri. It was as if someone had designed a textbook example of what an alien signal should look like. But science thrives on skepticism, and the initial euphoria soon collided with cold, hard scrutiny. The first red flag, the signal's frequency, 982 MHz, sits squarely in a band used by Earth satellites and aircraft. Researchers cross-referenced the detection with known sources of human-made interference, and the evidence grew damning. No other telescopes picked up BLC-1 despite repeated attempts. If this was a genuine extraterrestrial broadcast, why wasn't it visible elsewhere? Then came the clincher. Further analysis revealed the signal's drift rate wasn't consistent with Proxima Centauri B's orbit after all. Instead, it matched the movement of human-made electronics, likely a malfunctioning device or passing satellite somewhere near the observatory. The nail in the coffin arrived months later when researchers traced the signal's fingerprints to a set of cheap, consumer-grade electronics, the culprit. Probably a mobile phone, a Wi-Fi router, or even a poorly shielded computer near the telescope site. These devices can leak radio waves at surprisingly high power, and in the achingly sensitive ears of a modern radio telescope, they can masquerade as signals from the stars. Yet the BLC-1 saga wasn't a failure. It was a stress test for modern SETI. The signal passed initial filters because it was exactly what astronomers were trained to look for: narrowband, drifting, and originating from a star with a known habitable world. That it turned out to be terrestrial only underscores how clever and how insidious human interference has become. Our planet is now so saturated with radio noise that distinguishing a cosmic whisper from a smartphone's hum is like picking out a single voice in a crowded stadium. The lesson here isn't just about false alarms, it's about refinement. Every near miss like BLC-1 sharpens the tools and protocols used in the search. Future signals will face even tougher scrutiny, with cross-verification from multiple telescopes and advanced algorithms designed to weed out terrestrial imposters. And while BLC-1 may have been a bust, Proxima Centauri remains a prime target. A red dwarf star with at least 2 planets, one of them Earth-sized and temperate. It's the kind of place you'd aim a beacon if you wanted to be heard. So the search continues, not in disappointment but with renewed precision, because somewhere out there, buried in the static of the cosmos, might be a signal that doesn't fade under scrutiny, one that holds its frequency, repeats on schedule, and defies every earthly explanation. And when that day comes, the tools honed by false starts like BLC-1 will be the reason we recognize it for what it is. The irony of searching for signals from nearby stars is that their closeness makes them both the most promising targets and the hardest to verify. Proxima Centauri, a mere 4.2 light-years away, should be an ideal candidate. Its proximity means any signal wouldn't need to be overwhelmingly powerful to reach us. But this very closeness also puts it in the crosshairs of Earth's own radio cacophony. Our planet is drowning in noise, satellites, radar systems, even everyday devices like Wi-Fi routers and smartphones leak radio waves that can masquerade as extraterrestrial transmissions. The quieter the cosmos, the louder our own interference becomes. Take the case of BLC-1. Detected near Proxima Centauri, it ticked every box for an artificial signal, narrowband, drifting, and seemingly aligned with a habitable exoplanet's orbit. Yet its downfall was its plausibility. Signals from nearby stars are more likely to overlap with frequencies we've saturated with our own technology. A transmission from a galaxy billions of light-years away would face no such confusion. It's so distant. There's no chance it's a satellite glitch, but Proxima. It's practically in our backyard, sharing radio real estate with Earth's telecom traffic. This creates a paradox for SETI researchers. nearby stars are the best places to look for civilizations that might be physically reachable or communicable within a human lifetime. Yet every signal from them is suspect until proven otherwise. The closer the star, the higher the burden of proof. Scientists now employ a multi-step verification process. If a signal emerges from a nearby system, it must be detected by at least 2 telescopes on different continents, ruling out local interference. It must also exhibit properties no human technology can replicate, like pulsing in a mathematical sequence or emanating from a point in space that's moving with stellar precision. Compounding the challenge is the nature of red dwarf stars like Proxima Centauri. These small, turbulent stars are prone to violent flares that can scramble radio signals and mimic artificial patterns. A burst of stellar activity might briefly masquerade as a structured transmission, only to vanish when the flare subsides. This means even a seemingly clean signal from a red dwarf requires extra scrutiny. Is it a message or just the star's tantrum? Yet the allure of nearby stars keeps astronomers listening. Proxima Centauri b, with its Earth-like mass and temperate orbit, remains one of the most compelling targets in the galaxy. Future telescopes, like the Square Kilometre Array, aim to cut through the noise with unprecedented sensitivity, filtering out Earth's radio pollution like noise-canceling headphones for the cosmos. Until then, the search continues, a delicate dance between hope and skepticism, where every signal from a neighbor could be a greeting or just another echo of our own noisy civilization. The universe's greatest irony might be this: the voices we're straining to hear could be drowned out by our own. In July 2017, astronomers at the Arecibo Observatory, before its tragic collapse, were running a routine scan of nearby stars when their instruments picked up something bizarre. Ross 128, a dim red dwarf star just 11 light-years away, was emitting a strange signal. Unlike the usual cosmic noise, this one was a series of quasi-periodic pulses, drifting in frequency in a way that initially defied explanation. For 10 minutes, the star seemed to be broadcasting something almost rhythmic, as if it were sending a weak but deliberate transmission. The discovery sent shockwaves through the astronomy community. Here was a star, barely a cosmic stone's throw from Earth, behaving in a way no red dwarf should. At first glance, the signal ticked several tantalizing boxes. Ross 128 is known to host at least one exoplanet, though it orbits far too close to the star to be habitable. Still, the presence of one planet raises the possibility of others lurking in cooler, more life-friendly orbits. The signal's drifting frequency also matched what you'd expect from a transmitter on a rotating planet, its motion subtly tugging the signal's pitch like a cosmic Doppler effect. Even more intriguing was the signal's narrowband nature. Most natural astrophysical phenomena, like flares or stellar activity, produce broad, messy emissions. This was sharp, almost surgical in its precision, but science thrives on skepticism, and the initial excitement soon met rigorous scrutiny. The Arecibo team, led by Professor Abel Mendes, began methodically ruling out possibilities. Could it be stellar activity? Red dwarfs are notoriously volatile, prone to flares that can mimic artificial signals. Yet Ross 128 showed none of the usual signs of heightened activity during the observation. Next, they considered human-made interference satellites, aircraft, or ground-based transmitters. This was the most likely culprit, but the signal's origin appeared firmly tied to the star's position in the sky. For a brief, electrifying window, the possibility lingered. Was this it? Then came the breakthrough. Further analysis revealed the signal's telltale fingerprint. Its frequency drift wasn't consistent with a planet's rotation after all. Instead, it mirrored the movement of high Earth orbiting satellites, specifically those in geostationary orbit. These satellites drift slightly over time due to gravitational interactions with the Moon and Sun, and their signals can appear to move against the backdrop of stars. When researchers cross-referenced the observation time with satellite trajectories, the mystery unraveled. The signal wasn't from Ross 128, it was from our own technology, a satellite thousands of miles overhead, its radio emissions bouncing through the cosmos like a cosmic game of telephone. Yet the Ross 128 episode wasn't a dead end. It highlighted the growing challenges of modern SETI. The quieter the universe seems, the louder our own noise becomes. Every new satellite, every wireless device adds to the cacophony astronomers must filter out. But it also underscored something profound. Our tools are getting better. The fact that researchers could trace this signal back to a specific satellite in a specific orbit speaks to the precision of modern astronomy. Ross 128 remains a fascinating target. Its quiet stability makes it an ideal place to hunt for genuine signals. And while this particular detection turned out to be terrestrial, the star hasn't given up all its secrets yet. Future telescopes free from Earth's radio clutter might one day find something truly alien in its whispers. Until then, the Ross 128 signal stands as both a cautionary tale and a beacon of progress, a reminder that in the search for cosmic neighbors, every false alarm sharpens our ability to recognize the real thing. Ross 128 might have fooled us once, but astronomers keep coming back to stars like it for a simple reason. Red dwarfs are the most common stars in the Milky Way, outnumbering Sun-like stars 10 to 1. If we're searching for cosmic neighbors, ignoring them would be like hunting for fish in a pond while ignoring the ocean. These dim, cool stars burn so slowly they'll outlive the universe itself, offering civilizations vast stretches of time to arise, evolve, and perhaps reach for the stars. Yet for all their abundance, red dwarfs pose challenges that make them paradoxically fascinating. Hostile environments where life would need to defy the odds to survive, let alone thrive. Take the issue of tidal locking. Most planets orbiting red dwarfs are likely gravitationally locked, with one side permanently scorched by the star's faint glow and the other plunged in eternal night. A thin ribbon of twilight between these extremes might offer habitable real estate, but the conditions would be extreme howling winds as temperature differentials drive violent weather, or deep ice sheets creeping into the sunlit zone. Then there's the star's temperament. Red dwarfs are prone to apocalyptic flares, capable of stripping atmospheres from nearby worlds in a matter of centuries. Early in their lives, these stars can shine hundreds of times brighter than usual, bombarding planets with enough ultraviolet radiation to sterilize oceans. Yet life, if it exists, is nothing if not adaptable. Imagine microbial colonies huddling deep underground or beneath ice sheets, sheltered from the fury above. Or picture a civilization that's harnessed its stars' flares, storing their energy in vast orbital arrays. Some researchers even speculate that tidally locked planets might develop global ecosystems unlike anything on Earth, swirling algae-like organisms migrating with the Terminator line, or aerial life forms riding perpetual jet streams. The very extremity of these environments forces us to rethink what habitable even means. That's why SETI listens so intently to red dwarfs. A signal from a world like Proxima Centauri b or Ross 128 wouldn't just suggest life exists, it would prove life can endure conditions we'd consider uninhabitable. And because these stars are so numerous, a single detection would imply the galaxy could be teeming with civilizations we've overlooked, hidden in the shadows of faint crimson suns. Every false alarm, like the Ross 128 satellite glitch, refines the search, because someday a signal won't fade under scrutiny. It'll hold steady, defy explanation, and whisper the one thing we've longed to hear. We're not the only ones who have learned to shout into the cosmic dark. Gliese 581g might be one of the most controversial exoplanets ever discovered. A world that could be a rocky, temperate oasis or might not exist at all. Nestled in the habitable zone of its red dwarf star, 20 light-years away in the constellation Libra, this potential planet sparked headlines in 2010 when astronomers announced its detection based on subtle stellar wobbles. But what really sent shockwaves through the scientific community was the unconfirmed radio signal allegedly tied to it, a whisper of narrowband radio waves that some believed could be artificial. The story begins with a puzzling observation from the RATIAN 600 radio telescope in Russia. During a sweep of the Gliese 581 system in 2008, 2 years before the planet's official discovery, researchers recorded a brief but notable signal. Unlike the cosmic static of natural sources, this one was concentrated in a tight frequency range, the kind typically associated with intentional transmissions. Even more tantalizing, the signal appeared to originate from the direction of Gliese 581g, a planet that, if real, sits in the star's Goldilocks zone where temperatures might allow liquid water. Skeptics were quick to pounce. For starters, the planet itself is hotly debated. Some teams analyzing the same stellar wobbles found no evidence of Gliese 581g, suggesting it could be an artifact of noisy data. Without a confirmed planet, the signal's significance crumbles. Then there's the signal's fleeting nature. It was detected only once, never repeated, and no other observatories corroborated it. In the world of SETI, one-time events are almost always chalked up to interference. Glitches, satellites, even terrestrial microwave emissions have mimicked alien signals before. But here's where the plot thickens. The frequency of the signal, around 1420 MHz, holds symbolic weight. Astronomers call this the water hole, a quiet band between the natural radio emissions of hydrogen and hydroxyl molecules, the components of water. It's long been theorized as an ideal frequency for interstellar messaging, a cosmic meeting place where civilizations might gather to broadcast. If the signal was artificial, its choice of frequency could be a deliberate nod to universal chemistry, a way to say, we understand water just like you. The debate rages on. Could the signal have been a technical hiccup? Absolutely. The RATIAN 600 telescope, while powerful, is surrounded by human-made radio noise, and its single-dish design makes pinpointing exact celestial coordinates tricky. Yet the coincidences are hard to ignore. A narrowband signal in the water hole from a star system with a potential Earth-like world. It's the kind of alignment that fuels decades of scientific speculation. Even if Gliese 581g and its signal fade into obscurity, their legacy endures. They force us to confront the messy reality of cosmic exploration, where every detection teeters between breakthrough and blunder. And they remind us that the search for extraterrestrial intelligence isn't just about finding answers, it's about learning to ask the right questions, even when the universe replies in static. The concept of a habitable zone, sometimes called the Goldilocks zone, is deceptively simple. It's the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too close to the star where oceans would boil away, and not too far where they'd freeze solid. But when it comes to a planet like Gliese 581g, that simplicity unravels into a web of complexities. This potential world, if real, orbits at the inner edge of its star's habitable zone, bathing in crimson light from a sun 1/3 the size of our own. Red dwarfs like Gliese 581 are miserly with their warmth, meaning their habitable zones are scrunched in close, so close that any planets there risk being tidally locked, with one face perpetually scorched and the other shrouded in eternal night. That's the first twist in the habitable zone debate. Earth-like conditions might not require an Earth-like orbit. A tidally locked planet could harbor life in its twilight belt, where temperatures hover in a narrow band between extremes. Glaciers on the night side might slowly weep meltwater into the habitable strip, while volcanic activity along the terminator could provide heat and nutrients. Photosynthetic organisms, if they exist, might huddle in ring-like bands, tracking the faint glow of their dim sun. This isn't science fiction, it's astrobiology's cutting edge, where definitions of habitable stretch to accommodate the universe's creativity. Yet location is just the beginning. Gliese 581G's star is a volatile red dwarf prone to flares that can unleash torrents of ultraviolet radiation. For life to survive here, it would need a thick atmosphere to shield against stellar tantrums, or perhaps an underground refuge where microbes could weather the storm. Some researchers even speculate that tidal forces from the star might keep a planet's interior molten, fueling hydrothermal vents that could serve as oases for extremophiles. The takeaway: a planet in the habitable zone isn't guaranteed to be hospitable. It's merely a starting point, a roll of the cosmic dice where atmosphere, geology, and starry temperament all weigh in. This uncertainty is precisely why SETI zeroes in on such worlds. A signal from a planet like Gliese 581G wouldn't just hint at life, it would prove life can thrive in conditions we'd consider hostile. And if life can emerge there, clinging to the razor's edge of habitability, then the galaxy might be far more crowded than we've dared to hope. That's the gamble astronomers take every time they aim a telescope at a red dwarf's faint glow. The universe might not play by Earth's rules, and the voices we're straining to hear could be whispering from the unlikeliest of places. In May 2020, Russia's RATAN 600 radio telescope, a colossal ring of antennas nestled in the Caucasus Mountains, picked up a signal that sent ripples through the astronomy community. The source, a sun-like star named HD 164595, located 94 light-years away in the constellation Hercules. This wasn't just another cosmic blip. The signal clocked in at 11 GHz, a frequency with minimal natural interference, making it eerily reminiscent of what an artificial transmission might look like. Even more intriguing, the star had already been on astronomers' radar as the host of at least one Neptune-sized planet, raising the tantalizing question: could this be a technological signature from a civilization farther out in that system? The signal's brevity was both its allure and its frustration. It lasted just seconds, vanishing before other telescopes could swing into position to verify it. Initial analysis suggested it wasn't a flare or stellar activity. Sun-like stars like HD 164595 don't typically produce such narrowband bursts. The signal's intensity also raised eyebrows. To reach Earth with that strength, the transmitter would have needed to be unimaginably powerful, either a focused beacon aimed precisely at us or a planet-sized broadcast radiating in all directions. Either scenario stretched the limits of known physics or implied engineering far beyond human capability. Skeptics pounced on the lack of replication. In SETI, a single detection is little more than a cosmic mayfly, here one moment, gone the next, leaving no trace to study. Without independent confirmation from observatories like the Allen Telescope Array or Green Bank, the signal's credibility withered. Then came the kicker. Further scrutiny revealed the 11 GHz frequency is heavily used by Earth's military and communication satellites. The signal's drift rate, initially thought to hint at planetary motion, matched the wobble of high-orbit satellites instead. The most plausible explanation: a passing satellite or aircraft, its radio emissions bouncing off the telescope's dish like a cosmic echo. Yet the RATAN 600 anomaly lingers as a cautionary tale. It underscores how even the most promising signals can crumble under scrutiny, and how Earth's own technology now pollutes the radio spectrum to the point of mimicking alien contact. But it also highlights an uncomfortable truth: the quieter the universe seems, the louder our own noise becomes. Every satellite launch, every wireless device adds static to the cosmic radio dial, forcing astronomers to sift through an ever-thickening fog of human-made interference. The irony is exquisite. The same technology that fuels our search for extraterrestrial intelligence, the satellites linking global observatories, the algorithms parsing petabytes of data, also drowns out the very signals we're hunting for. HD 164595's phantom transmission serves as both a warning and a motivator. As we reach deeper into the cosmos, we'll need sharper tools, stricter filters, and a healthy dose of skepticism to separate the cosmic whispers from the noise of our own making. Until then, every unexplained blip remains a reminder not just of how much we don't know, but of how carefully we must listen. The RATAN 600 telescope is a relic of Soviet ambition, a sprawling, ring-shaped array of radio antennas built in the 1970s, nestled in the foothills of the Caucasus Mountains. Its design is almost alien by modern standards, a circular wall of nearly 900 movable panels reflecting radio waves onto a central receiver. Unlike sleek, computerized observatories of today, RATAN 600 operates with a kind of analog grit, requiring manual adjustments and painstaking calibration. Yet for all its age, this Cold War-era behemoth still plays a surprising role in the hunt for extraterrestrial intelligence. While newer telescopes might outperform it in precision, RATAN 600 offers something rarer: raw, unfiltered coverage of the sky, scanning vast swaths of the cosmos in sweeping arcs that modern narrow-field instruments often miss. What makes RATAN 600 uniquely valuable is its ability to detect signals across an exceptionally wide frequency range, from hundreds of megahertz up to tens of gigahertz. Most contemporary SETI projects focus on narrowband signals, the kind a civilization might deliberately broadcast, but RATAN 600's broad ears can catch the unexpected anomalies that don't fit neatly into predefined search parameters. It's the astronomical equivalent of a wide net trawl, pulling up oddities that more targeted surveys might overlook. This was how it spotted the now-debated signal from HD 164595, a blip that, for all its ambiguity, sparked global discussion precisely because it didn't behave like natural cosmic noise. Of course, the telescope's age comes with trade-offs. Its single-dish design makes pinpointing exact celestial coordinates tricky, a limitation that's led to false alarms and contested detections. Modern arrays like the Very Large Array in New Mexico or China's FRST telescope can triangulate signals with surgical precision, ruling out terrestrial interference in ways RATAN 600 simply can't. Yet there's an argument to be made for its persistence. In an era where radio astronomy is increasingly crowded by satellite constellations and ground-based interference, RATAN 600's remote location grants it a relative oasis of quiet. Its observations, though sometimes murky, provide a crucial counterpoint to the sterilized data of more advanced instruments. Perhaps the most compelling case for RATAN 600's continued use is philosophical. SETI has always been a game of probabilities, a bet that somewhere in the cosmic haystack a needle awaits. Newer telescopes are finely tuned to find needles that look the way we expect them to. But what if we're wrong? What if alien signals don't conform to our models? RATAN 600's strength lies in its willingness to listen broadly, to catch the outliers and the anomalies that might otherwise slip through the cracks. In that sense, it's less a relic than a safeguard, a reminder that the universe rarely follows our scripts, and that sometimes the answers we seek might come from the places we least expect. So while the latest SETI initiatives deploy machine learning and quantum computing to sift through petabytes of data, RATAN 600 hums along in the background, its dish turned toward the stars. It may not have the glamour of breakthrough listen or the resolution of the square-kilometer array, but in the grand, uncertain search for cosmic company, diversity of tools is just as vital as precision. After all, the first alien signal, if it ever comes, might not arrive in the form we've rehearsed. It might be a whisper in the static, a blip on an old printout, or a fleeting signal from a telescope that refused to retire. And when that day comes, even the quirkiest instruments in astronomy's arsenal will have their moment. In July 1967, a young astrophysicist named Jocelyn Bell Burnell was reviewing data from a new radio telescope near Cambridge when she noticed something bizarre. a series of precise, repeating pulses appearing every 1.337 seconds. The signal was so unnervingly regular it seemed artificial, ticking like a cosmic metronome with none of the randomness of natural cosmic noise. The pulses were dubbed LGM1, short for Little Green Men 1, a tongue-in-cheek nod to the unsettling possibility that we might have just intercepted an alien lighthouse. At first, the discovery sent shockwaves through the small team. The signal's rhythm was unlike anything observed before. Natural radio sources like quasars or supernova don't pulse with such machine-like precision. The team even quietly considered the idea that they'd stumbled upon a beacon, a deliberate transmission from a civilization far more advanced than our own. The implications were staggering. If true, this wasn't just a discovery, it was a watershed moment in human history, proof that we weren't alone in the universe. But science thrives on skepticism. Before announcing contact, the team ruled out terrestrial interference. Could it be a satellite, a radar echo, or even a prank? All were dismissed. The signal persisted, unwavering. Then came the breakthrough. Additional pulses were found elsewhere in the sky, all with similarly precise but slightly different intervals. The odds of multiple alien civilizations all using pulsating beacons at different rates seemed vanishingly small. The truth was far stranger. They discovered pulsars, rapidly spinning neutron stars emitting beams of radiation like cosmic lighthouses. The LGM1 episode became a turning point for SETI. It underscored the importance of methodical verification, teaching astronomers to temper excitement with rigorous scrutiny. False positives weren't just inevitable, they were valuable lessons in cosmic humility. The universe, it turns out, is full of natural phenomena that mimic artificial signals, magnetars flaring with clockwork precision, masers amplifying radio waves into laser-like beams, even distant galaxies pulsing in ways that defy easy explanation. Yet the legacy of LGM1 isn't just about caution. It's a reminder that the line between the extraordinary and the mundane is often thinner than we think. What began as a potential alien hello ended up revealing an entirely new class of celestial object, one that would earn a Nobel Prize and reshape our understanding of stellar evolution. The little green men turned out to be neutron stars, but for a brief, electrifying moment, they forced us to confront the thrilling uncertainty of the cosmos and the realization that sometimes the truth is stranger than anything we could invent. Pulsars are nature's ultimate imposters, cosmic objects so precise, so unnervingly rhythmic. They blur the line between natural phenomenon and engineered signal. These rapidly spinning neutron stars, born from the violent deaths of massive suns, beam radiation into space with the regularity of a Swiss watch. Some rotate hundreds of times per second, their lighthouse-like pulses arriving on Earth with such clockwork consistency that early observers seriously debated if they were alien transmissions. And that's precisely what makes them invaluable to the search for extraterrestrial intelligence. Pulsars are the universe's control experiment, a way to test our ability to distinguish the genuinely artificial from the merely extraordinary. Consider the Crab pulsar, nestled in the remnants of a supernova observed by Chinese astronomers in the year 1054. Every 33 milliseconds, like clockwork, it sends a pulse of radio waves sweeping past Earth. If you didn't know better, you might mistake it for a beacon, a deliberate signal from a civilization advanced enough to harness the energy of a dying star. But pulsars don't just mimic artificial signals, they outperform them. Their timing is so precise that astronomers use them as cosmic GPS, mapping the Milky Way's structure and even testing Einstein's theory of relativity by measuring how their pulses warp in the presence of gravitational fields. This reliability is why SETI scientists treat pulsars as both a challenge and a training ground. Every new pulsar discovery refines the algorithms used to sift through cosmic noise, teaching us what truly random looks like in a universe full of patterns. When the Breakthrough Listen project scans the skies, its software first filters out known pulsars, ensuring these natural metronomes don't trigger false alarms. But there's a deeper lesson here. Pulsars prove that the cosmos can produce phenomena indistinguishable from technology, at least at first glance. If nature can create something this precise, what other illusions might be waiting in the static? The answer lies in the details. While pulsars pulse with regularity, their signals bear subtle fingerprints of their origins. The radiation spreads across a range of frequencies, a telltale smear caused by electrons in interstellar space. Artificial signals, in contrast, tend to be narrowband focused like a laser beam on a single frequency. Pulsars also slow down over time, their spins gradually winding down as they bleed energy into space. A genuine alien beacon designed to last millennia might compensate for such decay, maintaining perfect timing in ways nature never could. Yet pulsars keep surprising us. Some, like the so-called Black Widow pulsars, orbit companion stars they slowly vaporize with their radiation, a cosmic horror story written in radio waves. Others, called millisecond pulsars, spin so fast they're essentially stellar gyroscopes, their stability rivaling atomic clocks. Each discovery expands our understanding of how bizarre the universe can be, forcing SETI to adapt. Because if we ever do find a signal that truly defies natural explanation, we'll need to be absolutely certain it's not just another cosmic mimic, another neutron star in disguise. In the end, pulsars are more than just false alarms, they're cosmic teachers. They remind us that the universe is stranger than our imagination, capable of crafting signals so perfect they seem intentional. And in that strangeness lies a paradox. The more we learn about nature's capacity for mimicry, the sharper our tools become for spotting the real thing. So when the next anomalous pulse crackles through a radio telescope, we'll have pulsars to thank for teaching us how to listen, not just to the noise but to the silence between the beats. Tabby's star isn't the only cosmic oddball casting shadows that defy easy explanation. Across the galaxy, astronomers have catalogued a growing menagerie of stars with bizarre dimming patterns, each one a potential alien megastructure candidate, though nature often conjures illusions just as captivating as any technological marvel. Take Epic 244543294, a young stellar system where light dips up to 80% far deeper than any known planet could cause. Then there's V1333 Cygni, whose erratic flickers resemble someone intermittently covering a flashlight with their hand. These aren't just anomalies, they're cosmic inkblot tests, revealing how quickly even seasoned scientists reach for extraordinary explanations when faced with the unfamiliar. What unites these stars isn't just their strangeness, it's the underlying pattern that makes them so compelling. Unlike predictable planetary transits or tidy eclipses, their light curves are jagged, asymmetrical, and sometimes achingly slow. Boyagian stars' 22% dips might seem dramatic, but they're dwarfed by stars like 2IC3 162917, where light plummets by 96% over weeks before rebounding. Such extreme behavior pushes natural explanations to their limits. Could swarms of comets really be this numerous? Would interstellar dust clouds drift in such geometrically odd configurations? The numbers strain credibility, yet so does invoking alien engineering without ironclad proof. This tension fuels the hunt for additional clues. One telling sign is infrared radiation, the thermal fingerprint of dust-absorbing starlight. When the Spitzer Space Telescope observed Boyagian's star during a dimming event, it detected excess infrared heat, tilting the scales toward natural explanations like circumstellar debris. Yet other stars show no such infrared excess, leaving room for speculation. Another key detail is color shift, whether dimming affects all light wavelengths equally. Natural dust tends to scatter blue light more than red, creating a telltale reddening effect during transits. Some candidate stars obey this rule, others dim evenly across the spectrum, as if shaded by something unnaturally opaque. The most provocative cases emerge when multiple strangenesses converge. Consider Gaia 16a, a star whose brightness yo-yos unpredictably, sometimes dipping in mere hours, far too fast for orbiting planets or even most dust clouds. Its light curves resemble someone flicking a celestial dimmer switch, with patterns so irregular they resist classification. Then there's ZTFJ 132047 plus 542400, whose light not only dims erratically but occasionally brightens beyond its normal baseline, as if reflecting focused beams back toward Earth. What makes these discoveries electrifying isn't just their peculiarity, it's what they imply about cosmic diversity. Human civilization has monitored stars seriously for barely 4 centuries, a blink in cosmic time. We're like ants trying to decipher Morse code by watching stadium lights flicker through frosted glass. Each anomalous star expands the repertoire of what's possible, forcing us to confront how little we truly understand about stellar behaviors and how quick we are to label alien what might simply be nature's next unveiling. Yet dismissing the megastructure hypothesis outright would be equally premature. The universe is 14 billion years old, plenty of time for intelligence to arise and reshape its surroundings in ways we can't yet fathom. Perhaps what we're seeing aren't fully built Dyson swarms, but construction sites, partial arrays, damaged megastructures, or even abandoned projects from civilizations long gone. The challenge lies in distinguishing engineering from astrophysics when both operate on scales beyond human experience. This ambiguity fuels next-generation tools like the Vera C. Rubin Observatory, set to survey the entire sky every few nights, catching transient events with unprecedented clarity. Its cameras might spot more stars behaving strangely, building a statistical picture of how often these anomalies occur. Meanwhile, projects like Breakthrough Watch are developing spectrographs to analyze starlight during dimming events, hunting for chemical signatures of artificial materials, unusual ratios of elements or molecules that wouldn't form naturally in space. The search thrives on this delicate balance between open-mindedness and skepticism, between nature's infinite variety and technology's signature. Every strange star is a riddle wrapped in a mystery, whispering that the cosmos still holds wonders beyond our current imagination. Whether these whispers come from natural phenomena or distant minds, their message is the same: keep looking up. Humanity's greatest strength, our relentless imagination, might also be our biggest blind spot when confronting cosmic mysteries. Every time we encounter an anomaly like Tabby's star or the WOW signal, we instinctively reach for explanations that mirror our own technological adolescence. We picture Dyson swarms because we've toyed with solar panels, envision alien lighthouses because we've built them ourselves. But what if intelligence a million years more advanced operates on principles we can't yet fathom? Our bias toward human-like solutions risks turning the search for extraterrestrial intelligence into a cosmic Rorschach test, projecting familiar patterns onto the unknown. Consider how often we default to radio waves as the gold standard for communication. Early SETI efforts focused on them because they slice neatly through interstellar dust and require relatively little energy to transmit. But that logic assumes other civilizations would follow the same technological trajectory, that they'd invent radio before more exotic methods, or even perceive the universe as we do. Imagine explaining fiber optics to a society that never discovered glass, or quantum entanglement to one still chiseling messages in stone. The truth is, we're searching for extraterrestrial intelligence using tools and theories rooted in Earth's 20th century physics, while the cosmos has had billions of years to birth civilizations that might communicate through neutrino pulses, gravitational wave modulation, or phenomena we haven't even named yet. This anthropocentric tether becomes even more apparent when we dissect so-called technosignatures. A Dyson Sphere is compelling because it aligns with our own energy needs, but a Kardashev Type II civilization might have long since abandoned such brute force methods. They could harness dark energy, manipulate spacetime to create quantum energy sinks, or exist as post-biological entities with negligible power requirements. Our fixation on megastructures might be as quaint as an ancient astronomer assuming alien worlds must have chariot tracks and torch-lit cities. Even our concept of signals feels increasingly archaic in an era where humanity itself is transitioning TOWRD, Chinese letter, Chinese letter, Chinese letter, Chinese letter, and AI-generated communication. What if advanced civilizations don't broadcast at all, but instead embed messages in the quantum foam of spacetime or the spin of entangled particles? The flip side of this bias is equally dangerous, dismissing anomalies too quickly because they don't match our expectations. When pulsars were first discovered, their precision nearly led astronomers to classify them as artificial. Today, we risk the opposite error, assuming nature can't possibly produce signals that mimic technology. Fast radio bursts were initially met with skepticism precisely because their properties seemed too engineered. This tug-of-war between overinterpretation and premature dismissal defines modern SETI. The middle path open-minded skepticism requires holding two contradictory ideas simultaneously: that the universe is unimaginably weird on its own, and that some of that weirdness might be intentionally crafted. Perhaps the most humbling realization is that our entire search might be looking in the wrong dimensional plane. String theorists posit 7 hidden spatial dimensions beyond our perception. A civilization mastering those could be signaling us in ways as imperceptible as a shadow passing through a wall. Their messages might be encoded in the slight variations of cosmic constants, the quantum spin of black holes, or even the branching probabilities of the multiverse. We're like flatfish scraping symbols on cave walls, unaware that the ocean exists. This isn't to discourage the search, far from it. Every dead end teaches us something new about physics, astronomy, and the limits of our assumptions. The key lies in diversifying our methods. Initiatives like Breakthrough Listen now scan for optical lasers alongside radio waves. Others hunt for thermodynamic anomalies, stars with waste heat signatures that defy known physics, or artifacts in our own solar system that might be billions of years old. Some researchers even propose looking for evidence of planetary scale engineering in the atmospheric chemistry of exoplanets, where industrial byproducts might linger like smoke from an unseen fire. Ultimately, the universe owes us no answers that fit neatly into human frameworks. The next great discovery might not come as a decipherable signal or a visible megastructure, but as a statistical anomaly in petabytes of data, a subtlety that only makes sense in hindsight. Recognizing this expands the search from a hunt for aliens to something grander, a stress test for the limits of our imagination, where every unexplained phenomenon is an invitation to dream bigger. After all, if we ever do find incontrovertible proof of intelligence beyond Earth, the greatest shock might not be that it exists, but how little it resembles anything we've dared to envision. In 1974, humanity took its first deliberate step into the cosmic conversation. From the massive dish of the Arecibo Observatory in Puerto Rico, astronomers beamed a 3-minute radio message toward the star cluster M13, 25,000 light-years away. Encoded in ones and zeros, the Arecibo message was a handshake, a primer on Earth's chemistry, DNA, our solar system, and even a crude stick figure of a human. It was never meant to be a serious attempt at contact. M13 was too distant for any conceivable reply, but rather a demonstration of human ingenuity. Yet 27 years later, in 2001, something astonishing appeared in an English wheat field. Near the Chilbolton Radio Telescope in Hampshire, a crop circle materialized overnight, bearing what looked like a direct response to the Arecibo transmission. The Chilbolton formation was unnervingly precise. Mimicking the original message grid-like structure, it replaced Earth's planetary diagram with a different solar system, swapped the human figure for a bulbous-headed alien silhouette, and altered the DNA double helix to include an extra strand details that seemed far too sophisticated for pranksters. Even the silicon-based element at the message core was replaced with silicon plus one unknown, hinting at exotic biochemistry. The timing was uncanny, arriving just as public fascination with crop circles peaked. Media outlets and UFO enthusiasts hailed it as proof we'd been answered not by radio waves, but by something or someone leaving clues in flattened barley. Skeptics, however, pointed to glaring inconsistencies. The real Arecibo message was transmitted at 2,380 MHz, a frequency crop circles couldn't possibly receive. The Chilbolton reply also contained errors in its binary code, suggesting human creators misinterpreting the original. Most damningly, crop circles had a well-documented history of being hoaxed. Teams like Doug Bauer and Dave Chorley had already confessed to creating hundreds using planks and ropes in the 1970s and 80s. The Chilbolton formation's precision, while impressive, fit neatly within the capabilities of skilled artists armed with GPS and geometric designs. Yet the allure persists. Why? Because the Arecibo message embodies a paradox at the heart of SETI, our longing for contact clashes with the universe's vast indifference. The original transmission won't reach its target for another 24,000 years. Even if M13 harbors a civilization capable of decoding it, their reply wouldn't arrive for 50,000 years total. The Chilbolton hoax tapped into something deeper, a hunger for immediacy, for proof we're not shouting into the void. It's no accident the reply appeared near a radio telescope, a symbolic echo of our own efforts, reflecting humanity's hope that the cosmos might answer on our timescale, not its own. The truth is less dramatic but no less fascinating. No confirmed response to the Arecibo message exists because physics itself stands in the way. Radio signals weaken with distance, diffusing into the background noise of the universe. Even if another civilization intercepted our transmission, distinguishing it from natural static would require technology we can barely imagine, and that's assuming they're listening at all. The Chilbolton formation, for all its artistry, was a Rorschach test, a canvas where we projected our cosmic loneliness onto a field of wheat. Still, the legacy of both the message and its faux reply endures. They remind us that the search for extraterrestrial intelligence isn't just about antennas and algorithms, it's about storytelling. Whether through radio waves or crop circles, we're crafting narratives to make sense of our place in the universe. And perhaps that's the real message. Until the day a genuine signal arrives, we'll keep finding or fabricating ways to feel less alone under the stars. The Arecibo message wasn't just a scientific experiment, it was a philosophical gamble. By deliberately beaming our coordinates and biological blueprints into space, we crossed a threshold, transitioning from passive listeners to active participants in the cosmic conversation. But was that wise? The debate over active SETI, the intentional transmission of signals to extraterrestrial civilizations, divides scientists like few other topics in astrobiology. On one side, proponents argue that hiding is both futile and counter to humanity's exploratory spirit. After all, our radio and television broadcasts have already leaked into space for over a century, painting a faint but detectable portrait of our presence. Why not replace that noise with something deliberate, something that says we're here and we're curious? But critics, including luminaries like Stephen Hawking, warn that advertising our existence could be catastrophically naive. Hawking famously compared active SETI to shouting into a jungle without knowing what predators might be listening. History, after all, is littered with civilizations undone by encounters with more advanced societies. If a technologically superior species detected our signals, their intentions, whether benign or exploitative, would be entirely beyond our control. The grim reality is that spacefaring civilizations, if they exist, might operate under ethical frameworks we can't comprehend. They could view Earth as a resource-rich frontier, or worse, an inconsequential ant-hill in the path of their cosmic ambitions. The ethical quandary deepens when you consider the scale of the gamble. Active SETI decisions are made by a handful of researchers, yet the consequences would ripple across all of humanity and potentially all future generations. Unlike climate change or nuclear disarmament, there's no undo button for an interstellar message. Once sent, it can't be recalled. This asymmetry has led some to argue that such transmissions should require global consensus, not just the approval of a small team with access to a radio telescope. After all, if a reply ever came, it wouldn't be addressed to a single nation or institution, but to our entire species. Yet the counterarguments are equally compelling. Passivity, some argue, is its own form of risk. If every civilization in the universe chooses silence out of fear, the cosmos becomes a library where no one dares speak. By reaching out, we might catalyze a network of cosmic communication, unlocking knowledge that could solve existential threats like energy scarcity or disease. There's also the moral dimension. If advanced civilizations exist, might they view our silence not as prudence but as a failure of courage? The universe has given us the tools to listen and speak. To withhold our voice could be seen as a rejection of that cosmic gift. The tension between these views shapes modern SETI policy. Initiatives like METI messaging extraterrestrial intelligence continue to broadcast carefully crafted messages, while others, like the Breakthrough Listen project, focus solely on passive observation. The divide even spills into pop culture. Films like Arrival and Contact dramatize the stakes, imagining first contact as both transcendent and terrifying. But fiction aside, the core question remains unanswered. Is the potential reward of cosmic connection worth the existential risk? Perhaps the most sobering perspective comes from the Fermi paradox itself. If the universe is teeming with life, why haven't we heard from anyone? One chilling possibility is that advanced civilizations do exist. They've just learned the hard way that broadcasting your location is a recipe for disaster. The silence we perceive might not be the absence of others, but the remnants of civilizations that once shouted into the dark, only to meet something they couldn't survive. Or maybe the truth is simpler. Space is vast and signals fade. The odds of a hostile civilization intercepting our messages, let alone caring enough to act, are vanishingly small. In that case, active SETI isn't reckless, it's optimistic, a bet that the universe is more wonder than warning. Until we know for sure, the debate will rage on, a testament to humanity's dual nature, part explorer, part survivor, forever torn between the urge to reach out and the instinct to hide. From the enigmatic wow signal to the rhythmic pulses of fast radio bursts, these 25 cosmic whispers represent more than just scientific curiosities. They're fragments of a much larger conversation. Each one challenges our understanding of the universe, dangling between natural phenomena and potential fingerprints of intelligence. Consider the eerie precision of SETI-02 plus 14a, drifting like a calling card from Pisces, or the tantalizing gaps in Tabby's star's light curve that stubbornly resist easy explanation. Even the false alarms, the satellite glitches masquerading as alien hellos, teach us something profound. The universe is a master of disguise, capable of crafting signals so uncanny they blur the line between the miraculous and the mundane. What unites these mysteries isn't just their strangeness, but the questions they force us to confront. Could the repeating bursts from FRB 121102 be the exhaust trails of an interstellar engine? Might be LC1, though debunked, hint at the kind of interference we'll need to filter out to hear a genuine signal. The search for extraterrestrial life isn't a straight path. It's a winding road where every dead end sharpens our tools and every anomaly stretches our imagination. This dance between skepticism and wonder is the heartbeat of SETI. Too much skepticism, and we risk dismissing the very thing we're seeking. Too much wonder, and we might mistake a comet's whisper for a cosmic hello. The implications ripple far beyond astronomy. Every unexplained signal is a mirror reflecting humanity's deepest hopes and fears. Are we alone, or is the universe humming with voices we've yet to decipher? The answer, whatever it may be, rewrites our place in the cosmos. Until then, the hunt continues not just with radio telescopes and algorithms, but with something far more essential: curiosity. The universe is under no obligation to make sense to us, yet here we are, ears pressed to the static, listening for a pattern in the noise, so keep looking up. Maybe you'll be the one to spot the next anomaly, or maybe the great revelation is still generations away. Either way, the act of searching itself is a tribute to what makes us human, the audacity to ask, is anyone out there? And the patience to wait for an answer. If you found these cosmic mysteries as thrilling as we have, don't stop here. Hit subscribe to join us on the next leg of this journey, and drop a comment below. Which signal do you think holds the most promise? The universe is vast, but the conversation is just beginning.